The talk will not be very technical because my experience is if you get too technical, you lose everybody in 2 slides and it's use. But where should I stand so you can see?
No. I just want to be straight.
So I need to position myself in a way that both you and Koma can see what's going on.
You're perfect. Your position is perfect.
Maybe I should be here.
Yes, this is better.
It works. Sorry, all of this is on the recording.
Oh.
Sorry, online audience. Yeah, it's very much on the concepts and the procedures of how you tackle the meta-analysis. So this is, thank you, Sabine. This is very much based on experience, not so much on statistical theory. But before I get into meta-analysis, I will say a few words on more the philosophy of doing research. Why the heck do we do research? What do you think? Why do we do research?
To create more knowledge.
Yeah, to increase knowledge.
Answer questions.
Answer questions, yeah.
Solve problems.
Solve problems, yeah, very good. Yeah. There's some other maybe less elevated motives to do research.
Because it's fun.
Oh yeah, it's fun. Yeah.
Top time.
Yeah. I think many of us like to build a career and have an income. This is a way to earn a living. But basically, doing research is very much indeed about obtaining knowledge and solving problems. And when we need a new idea, this is actually a quote from Fuso, because he will say approximately every second meeting he has with his group members, we need new idea, because he gets very bored with all the old ideas that people are putting forward for research. Because if you want to do interesting research, you should not ask the same question that other people have asked before. And when you write a paper about your research, actually you will need to explain how your research answers a question that was not answered before. Yeah.
I have a question about this. But one of the, curious about your opinion, one of the main things of pillars of science is reproducibility.
Yes.
But also verify the robustness of it. But like if you have this high impact journal and stuff, they always want something that's not been done before.
Yes.
While reproducibility is so important, but they don't want reproduced work.
Yes.
That's yeah. What's your opinion?
It's an excellent point. I think the microphone picks this up right, because it's true. To be actually certain about something, we need a result not from one research group which maybe has just the wrong test animal or the wrong environment, or has an interest in getting a certain result. We want to have results from multiple groups to see the robustness of a finding, so reproducibility and confirmation and rejection. That's very much in the scientific process. It's not how you get a paper in Nature. You get a paper in Nature, but if you really stumble on something that was totally unexpected. Of course, you can find that when you try to do confirmatory research and you find something very unexpected and you publish it. But usually, you get something very innovative by actually having a new idea. So it's that conflict. I think it's a conflict there. Any other opinions?
Well, in addition, maybe that it's useful to know that these days, also in grant applications, the role of high impact journal papers is getting less and less, depending on the funder. So more and more people are looking at the story, at the intended impact and the feasibility and stuff like that. Next to also, have you been able to publish papers in decent journals, of course. So perhaps this also helps in making this conflict a little bit smaller. But this will take a lot of time because it's not in culture of many scientists. Yeah.
But on the other hand, if you read the literature, probably when you're reading literature, you will think, oh, this is just the same type of work I've already read. I've already read 3 or 4 papers like this. This paper is less interesting because of that. So in a way, it's very much human nature. Anyhow, all the time we try to ask new questions to solve problems that are unsolved. Otherwise, we ask ourselves, why the heck am I doing that? Has already been done. It's about the meaning of life. What is actually research? I like definitions because it's very not so good to talk about concepts without defining what they actually mean. And Google is our friend. So Google brings us to dictionaries. So Cambridge Dictionary, Merriam-Webster Dictionary. And you find different definitions of research. So it's a detailed study of the subject, especially in order to discover new information or reach a new understanding. Investigation or experimentation aimed at the discovery and interpretation of facts, revision of accepted theories or laws in the light of new facts, or practical application of such new or revised theories or laws. So many different types of research to build theory or to actually test predictions from theory. So that's very, very according to Popper. So that you have induction and deduction going from a general principle to a specific prediction back to whether that general principle is actually true or not. And here is is a very hands-off one. Collecting information is also a research. But I think most of us will like more the first 2 definitions, where there is a connection between collecting information and having an understanding. And having an understanding, it really means that we have a model of the world in our head. And that model allows us to predict. It's very important to, if you write papers, to motivate your research. You cannot just say, we studied this or that without explaining why you did this or that. You can go and study maize soybean intercropping, but there are already 200, 300, 400 papers in the literature about maize soybean intercropping. So why do you need to investigate that? It needs a rationale. I don't think our students are very well trained in developing rationale in general, but it really means building a story to explain to the reader or the listener that what you're setting out to tell them is something that is not known because it has not been done before, and it has an importance for the real world in one way or another, or in the theory of a certain field. I have some terminology that I borrowed from a book. Is this book, The Craft of Research by Booth and Coulomb. They talk about a topic. It's just your general subject area. Maybe it is maize soybean intercropping in Indonesia. And then, then you need a problem. You cannot just say, okay, I studied this. There needs to be something about maize soybean intercropping that you feel is an issue. Maybe you say the issue is we don't know about its productivity, but then you need to think, can we not predict the productivity of maize soybean intercropping based upon what we already know from maize soybean intercropping in Tanzania and Kenya, similar latitudes? Then you need to explain what is so different in Indonesia to other countries that we still need to study that. Or maybe you want to say, based upon what we already know from maize soybean intercropping, we can make a prediction how it will perform here. And we want to check whether that is true or not, or it works out differently. So that's more like what Robert said in the confirmatory domain, where you want to verify that a certain theory is correct. But it always needs to be formulated as a problem. If readers don't see a problem in your introduction, they think, why the heck am I reading this? It needs to result in a research question, and the research question is just a concise way to tell the reader what you're after. And it could be we want to know whether soybean intercropping has a land use advantage under the circumstances that are prevalent in Indonesia. But you will need to explain what those circumstances are and how similar or different they are compared to the rest of the world. And yeah, this is related to the rationale, why it is worthwhile. So the research question, actually the rationale, maybe I put it in the wrong place there, but it comes before the research question. It comes between the problem, where you explain what the problem is, and that evolves into explaining why you have a question. You can read about it in this book. The book is a bit wordy, but I think it gives words to these concepts, and I think it's very important when you're writing papers. Well, how do we do something new in research? There are different ways. You can choose a different topic, or you can identify a new problem within the topic area. Or you can ask a new question that is related to a problem that was studied before. Or you can tackle the question with a new method, or the problem with a new method, or you can choose a new study system. When you're doing these novelties, you will need to explain, and that is what you need in proposals, is the scope to get new insights, things that you learn about the real world, and the scope to solve a real world problem is maybe equally important. The importance is shifting. Nowadays it's more important in grant proposals than it used to be before. And when you propose to do something new in research, you're always thinking yourself. And this is a list that I made for myself very early on during my career, when my chairman said, you need to think of a topic to work on. Oh, okay. What are my criteria to choose a topic? Well, you need to consider your own expertise. What are you good at? I wouldn't choose anything that's related to molecular biology, because no way. I would choose something related to modeling, to data analysis. Relevance, very important, whether it's important in the real world, and novelty, whether the scope to get something newness. And then, of course, you need to think about, can I do that? Do we have the capacity in our group? Do we have the resources? Is our farm large enough? Do we have the equipment? Is it not too costly? So all these things come in. And now I finally come to meta-analysis, because meta-analysis is analysis of existing data. And well, you might think analysis of existing data is just you calculate the average and that's it. So that is nothing new. Maybe it's relevant, but it's nothing new. And actually, it's not like that, because the activity of synthesis will also result in new knowledge that was not available before, because there can be hundreds of papers on intercropping and land equivalent ratio. But before anybody actually makes the effort of calculating the average land equivalent ratio and trying to find out which factors are driving the value of the land equivalent ratio across the studies, unless that has been done, we don't know that. Some people with a lot of experience have an idea. Maybe they write a narrative review on it. So in the early days, there is a person, Willie. I never met him. I don't know who he is, but he wrote some very good papers. Worked at Ikristat in India. Very insightful on what type of intercropping systems is productive. It was in the 1980s. But he's writing from his experience. You can believe him or you cannot believe him. There's not a whole lot of evidence in his storytelling. I totally believe him. He is summarizing what he has seen. But meta-analysis can be more convincing. Well, between meta-analysis and a story like Willie told is a narrative review. So you write a story, you cite all the what you consider the relevant publications, and you organize the knowledge in sections, in paragraphs, and you write a synthesis paper. And people may love that, very useful. But somebody else writes a narrative review. They can write a totally different narrative review because they have a different opinion on the subject. And this is why meta-analysis has emerged. Meta-analysis has emerged in the medical sciences, where there are very different points of view. There may be an industry point of view, which is actually inspired also by interest of industry. And there might be a researcher point of view. So industry will try to, pharmaceutical industry, I mean, they will try to find new remedies for diseases. And usually they will do small-scale trials to see if it works. And at some point, after having tried the treatment with maybe 20 subjects receiving the treatment, 20 subjects not receiving the treatment, they may already publish an early paper saying it works, because in the treatment group, 14 out of 20 get better. In the non-treatment group, 8 of 20 get better. It's a significant result. Okay, but that's a small study. And then you get into, indeed, this business of confirmation, where in medical studies, I think it is more accepted to repeat the study, but usually it will still be motivated by newness and relevance, because it will say the previous study was using a subject, white males in the USA aged 40 to 60. And then it's easy to motivate your study. We will do it for white females. And then next thing is, no, we will include African Americans in the same age category, and younger people. And there is a lot of this kind of differentiation in studies. And then you get this pile of data, and you try to wade through it and make up your mind, what does it mean? And this is where meta-analysis comes in. Because you have studies with different populations, you have studies of very different size. Maybe one study funded by industry has just 40 people being treated or not treated, and maybe there's a big government funded study that wants to have the final answer once and for all, and they have 5,000 people across whole America. And then how do you do that? Well, you need statistics, and it's the statistics of meta-analysis in a way is not so special, as mostly we use mixed effects models. Who has experience with mixed effects models? Actually, it's still a minority. Okay, all of you need to get exposed to mixed effects models for data analysis. They're almost indispensable these days, and they can be weighted or non-weighted, where you take into account whether your data has a high variance or a low variance, and then data with a low variance gets a bigger weight. There's standard methodology for that. It's actually very easy to implement in R. It's nothing really special. So that's what meta-analysis is. So we do it to synthesize the existing knowledge, but synthesize goes beyond calculating the simple average. It also includes finding overarching patterns. So maybe you would come to the conclusion that this treatment really works better in males than in females, or we need, if we look at the dose response, the optimum dose is different for males and females, and is different for Caucasian Americans and Black Americans, and there is no end to the differentiation that you will find in meta-analysis. And then actually you're doing something totally new, because the previous studies do not analyze all the data, so they will not get this insight of the effect of the subpopulations that you studied. Okay, so what is actually meta-analysis? So Meta is a Greek word, and it means beyond, above. So it's an above analysis. And I think the word overarching analysis is almost synonym with meta analysis. Meta-X means X about X, so metadata is data about data. Meta-analysis is an analysis of previous analysis or an analysis of previously collected data. Now, I talked a bit about a narrative review, where an author with experience, or maybe with not a lot of experience, goes and selects relevant papers from the literature and writes a story. It's a synthesis, but the review is not systematic usually. In a narrative review, you don't have to write in your method section how you selected your papers. But in a meta-analysis papers, you do have to explain how you found your papers and how you selected your papers, because and this comes from the medical field, because in the medical field there's always a degree of distrust whether people will leave out information that will contradict that the remedy works. So if industry is publishing certain data, it's very interesting, but they have an interest to show that the remedy works. We could suspect researchers working on intercropping have an interest to show that intercropping works, because you write 3 papers, intercropping has no yield advantage, is not improving resource use efficiency, and does not reduce diseases, then next thing is you have to find a different topic to work on, because now you've shown that intercropping doesn't work, so you're out of business. So even researchers have an interest. And socially, I think you can find that researchers can be extremely invested in their theory and absolutely unwilling to admit that actually they were wrong. I think there's no way for Phil Pickett or Kahn to say push-pull didn't work the way we thought. The volatiles are not important there. There's no way. They cannot admit that, because their career is built on this. So, I mean, when you come to research, you may think this is a very objective activity and people watch the evidence, but not necessarily. Not necessarily at all. So systematic review is actually very important. Of course, it's a tricky business because we can systematically review the literature, but how can we be sure that all the relevant information was published? Maybe some information was left out. This does come in the meta-analysis process, that there are some techniques, not very powerful techniques, but there are some techniques to find out whether certain information has not been published. And it's quite interesting. I had a conversation with Tang Li Tan, is a former PhD student, a colleague at China Agricultural University, and we were talking about the meta-analysis that we had done, and I said, we found no evidence for publication bias. This is called publication bias. If your result is different from the truth because some information has not been published and is not included in your analysis because you cannot find it because it has not been published. So I said, we did not find evidence for publication bias, and he almost fell off his chair laughing, because they said, of course there is publication bias. Don't you remember that we did not get this paper published? It's absolutely true. There in the review process of papers, you can often find that papers that are not confirming what is generally thought, that they will not get published, particularly if the study was not very strong. Then reviewers will say, I'm really not convinced this result is right. There are some weaknesses in the study design. Let's not publish this. But it means that certain studies, which are not very large maybe in sample size, and have a negative result, are missing from your database. It's a bit a side issue, but I tell it because even systematic review is not a guarantee you find all the relevant data. You can find all the relevant published data. That is what we should try and do. And this is very important. And so every meta-analysis paper has methods that explain which databases we searched, when we searched it, what keywords we used, and how we selected from the papers that we found. Because we need to make it clear that the information we collect and the information that we're analyzing is a representative sample of the population of interest. And by detailing our methods and making it very clear, people can understand what our population is. Yes.
Do you need all the raw data?
No.
I was kind of imagine that it's real difficult to get.
Usually we analyze what has been printed, what is in the figures or what is in the tables. But sometimes people go out and identify the papers that are relevant, and then they contact the authors and try to get the raw data. This is more work, but it's more powerful because you get better information. It's possible. Both is possible, and in some fields, authors are pretty willing to collaborate. So we have one meta-analysis on decomposition of mixed litter compared to single litters, and the authors were pretty fast in delivering their data. And yeah, we could do a better analysis with higher power. Yes. So what are the steps in the meta-analysis? So this is the procedure part. As usual, we start with a research question. Well, you already know in your introduction, you need to motivate your research question because it cannot drop out of the air. But for the meta-analysis, the research question is the starting point. Then we need to think about possible metrics to express the quantities of interest. This could, and you need to think about both the dependent variables, so the response variables, and the independent variables, the explanatory variables. So maybe we are interested in a land equivalent ratio, or maybe we are interested in the net effect of intercropping, the difference between the actual yield and the expected yield, or maybe we're interested in the relative fertilizer use efficiency of intercropping. There are many metrics we could be interested in. And then we also need to think about the independent variables, such as the fertilizer input, the sowing dates, and the temporal overlap between the species, the planting pattern of the species, maybe the environment, whether it's tropical, subtropical, arid, semi-arid, oceanic. We need to think about these, phosphorus content in the soil. Need to think about those variables. Actually, in meta-analysis, we hardly ever calculate yield because yield is because usually in a meta-analysis we do analysis across species, and if you go across species, then the yield is extremely variable according to the product. So maybe maize will give you 12 tons per hectare. If you harvest alfalfa and you just are interested in the biomass, maybe you can get 20 tons per hectare. If you have cottonwood, you have 2 tons per hectare. So oftentimes in meta-analysis, you use relative metrics comparing a treatment and a standard, and in intercropping, comparing the intercrop to the sow crops. So you standardize away the differences between the studies according to what their response variables were. Making things relative is a very powerful way to get rid of variability between studies and between different measured variables. One of the big surprises for me when first starting on meta-analysis was that it's actually possible to analyze this type of data. So previously, when we're trained doing statistics, we are told you cannot have one response variable is maize yield, and the other variable is wheat yield, and have it in one analysis. It doesn't make sense. It's a different variable. But that's exactly what we do in meta-analysis. But we solve it by making things relative. This is a different mindset in meta-analysis, that we can analyze things across different crops by making it relative. Okay, so if actually this is a long process to think about the question about the metrics and define the scope, whether it's worldwide or maybe you want to do it for China or for Africa and China to compare them, or just for Indonesia or for the tropics. You need to define the scope. And you might also say, I want to do it only for strip intercropping systems, or only for fully mixed systems, or only for organic systems. This is all related to the scope, which is immediately related to your research question. And the scope and your research question and your metrics, they determine what information you need. And then you need to develop a search strategy that will find all the available papers that have the data that you need. Yes.
Before you find the scope, you already check if there's enough literature available to answer a question within that scope?
Yeah, it's a very good question. So I would say that at a later point, but actually this linear process is not linear. It actually goes around in circles, because you develop a search strategy and you find the papers, and you get almost a heart attack because you find 5,000 papers. You cannot deal with 5,000 papers. Or in another instance, you do the search strategy, you find 3 papers. Neither of them is working. So you do the search, and then you think, hey, I need to do something about my scope, because I cannot work with this number of papers. There's just not enough information, or there's too much information.
What's an optimal number of papers per meta-analysis?
The number of papers, that's a trade-off between the quality of your analysis. More papers is better. The more papers, the stronger, the greater power, and the time it takes. More papers means more time. In practice, I will give examples. Our first PhD student working on meta-analysis, Yu Yang, he did his whole PhD thesis, about 3/4 of it with 100 papers. And then after Yu Yang had made his database, he first published a paper based upon 100 of those papers, and then he made a subset of only the cereal legume intercrops in his original database. That was 70 papers, and he formulated a different research question and answered it with this sub-database. And Chunji later on she added papers to the database of Yu Yang, getting 170 papers in total. And she redid part of the analysis of Yu Yang, but also did some additional analysis. And then by piling up data sets, actually, you can get stronger analysis and not spend too much more time. But 100 is a nice number, but you can easily get a meta-analysis published based upon 50, 60, 70 papers. If you go down to 15 papers, you get in the danger zone. Then reviewers may tell you, you need to enlarge your scope and make it more interesting. We have one paper on crop yields in agroforestry systems in Europe, and it's based on 15 papers. And we had to try many journals to get it published. And one of the reviewers on one occasion said, oh, you need to include agroforestry systems from the US. There's at least 100 extra papers there. But we were not interested in the agroforestry systems in the US. We wanted to know what do we know about Europe? So that was not our question. So we were unwilling to enlarge the scope. We also didn't have the time. So no. So you do the search, and the search will tell you whether there's data and whether it's too much data or not enough data. You start extracting. which means reading the paper and putting the data in the database, and you really need to think about your variables, and you make columns, and a lot of this, in my experience, in the intercropping field at least, is explorative. So reading the papers makes you aware what information is in the papers, and then you start to extract it, which means that there is an iteration there, that you go back to papers that you extracted previously, and because you realize there's something very interesting that I should extract here, I forgot to extract it. So you need to go back. Very annoying, but totally normal. Actually, in the medical sciences, they have taken the next step, where they say, actually, you need to submit and publish your protocol for meta-analysis before you do it. So you need to think everything through before you actually carry it out. So you can publish the paper on your protocol, and then you can publish the paper on your results. In agronomy, ecology, this is not required. Fortunately, we are hardly aware that this development exists in the medical field. It exists in the medical field because they are probably 20 years ahead. They have very strongly developed methods, and so for certain types of meta-analysis, there really is I think it's possible to submit that protocol. But my experience in the intercropping field is we learned so much during the extraction and the reading and the first analysis that I really wouldn't like to submit my protocol and just follow the protocol when publishing my paper, because we discover too much while doing the work. So that's my opinion. But I work a lot with David Markowski, who is a statistician, and he will probably say it's a very good idea to publish the protocol first, because it gives a very rigorous procedure. But I just cannot think well enough ahead of time without having any data, because working with the data gives you lots of ideas. Then, extracting the data, there's software to actually extract the data from figures. And then you start analyzing, which is mostly just pretty basic statistics. And there is iteration, because you analyze the data and you realize maybe a somewhat different metric would be better. And then you need to go back to the papers to extract that data. Or maybe you realize you need different papers. So you can go back and redefine your research question and your metrics and your scope and everything at any point in this linear chain, as far as I'm concerned. But this is the protocol. You've seen this. This is intercropping, and this is the first meta-analysis that we were involved in Wageningen. This is the thesis of Yu Yang. He was just a boy when he started, and he
was an old man when he finished.
He was a lot wiser. When did he graduate? 2016, something?
Yeah.
Yeah, so I think he started 2012 approximately. So 12 years ago, and we basically knew nothing about meta-analysis. It was totally new to us. The only thing we knew is that I did not know the average land equivalent ratio of intercropping across the world. I only knew that there's a lot of papers that say intercropping is great and land equivalent ratio is high. But how high? Nobody would tell me, because it was not known. So somebody needed to wade through that literature, and at that time there were something like 3,000 papers. I think by now that has more than doubled. So the literature, if we actually want to analyze all the available data, I think we need software methods. We need AI to actually find the papers and extract the data from papers, and we are not there at all. I don't know if that will ever work, but the mountain of papers was already too big at that time, and we had no idea how many papers we would be able to extract. David Markowski, who had experience, said, "Oh, you can probably extract 2 papers per day." But Yu Yang actually, in 3 years of this process of 10 steps, in 3 years, in the end, he had 100 papers, and I think that was a hard job for him.
But why would it take like a whole day to extract 2 papers? What's the?
Oh, you need to read them carefully and extract the numbers. Half a day for 1 paper. You think it's too small?
No, but yeah, depends if you. How yeah, no, if you're right. I was more thinking about reading them, doing more scan them, and then use the data from there. But if you could.
It's very risky to just scan them. Scanning is only possible when in a field there is a very strong homogeneity in what people publish and how they call it. Now, LER, I think there is mostly consensus what the LER is, so you can extract it from the papers without much thinking. However, a lot of papers don't report the LER, they will report the yields. And as soon as they start to report the yields, you need to be extremely careful, because some papers report yields in intercropping per unit area of the whole intercrop. That is actually the consensus to do it that way. But in some cases, and Li Long always does that, researchers report the yield per unit area of the species in the intercrop. And then you need to know what is the area of the species. So if you have the system with maize at 50 centimeter and soybean at 50 centimeter, everything is 50 centimeter, you can just count the rows, it's easy. But as soon as people start to move the rows in space and have different row distances, it becomes very complicated to know what is the space for maize, what is the space for soybean. You need rules for yourself to do that. Trinji and I spent a lot of time how to define the proportion of the land use for one species and for the other species in the intercropping studies done in China, because they play a lot with the configuration. And so she has a 20-page supplementary information on how she extracted the data for one particular paper. So land equivalent ratio, and then just to remind you what land equivalent ratio is, you've seen this picture before. This is wheat and this is cotton. It's the same system. It's a relay system, and it has in the sow crops these yields, but the intercrop it has these relative yields, and then this is the land equivalent ratio, what it means, and this is the value of the land equivalent ratio across studies. I think this is actually not the final result of Yu Yang. I think this is halfway. So you can already see your results building up, and then you can say, well, this is enough papers or it's not enough papers. You can play with that. So there is a distribution, and why would there be so much variation in the LER? What do you think?
Different crops, different regions.
Yeah.
Different soil types.
Yeah. But I mean, people have been publishing LERs to 0.4. What's going on? Is that true? Actually, you cannot answer without carefully reading the paper whether the 0.4 is a true value. Maybe they have an intercrop that by intercropping one species totally does not produce yield. For instance, with maize peanut intercropping, there is shading of maize to peanut, and the peanut hates it. And peanut has a fruit that needs to penetrate into the soil to make this nice pot with the peanuts in it. You need to penetrate, but to penetrate, the plant needs to have some strength. But if the plant is shaded, it doesn't have the strength. So then it cannot, what they call, peg into the soil. You might not get any yield. if your maize is benefiting a lot from the space that's available because the peanut does not perform, maybe your land equivalent ratio is 0.7. But if there's semantic constraint in the maize, it could be possible that there is an intercropping system that gives you an LER of 0.4. It's also possible that you have an intercropping system that gives you an LER of 1.8. But I have difficulty I have doubts at both sides. So how do you decide that? Well, I advise my students to never exclude data because they're outliers, because an outlier can only be excluded if you believe it's a mistake, it's a reporting error. So you need to go back to the paper, see what they did is actually within the scope of what you're trying to do. And if it's within the scope of what you're trying to do, and if they did what they are supposed to do, and it's not obviously a reporting error, and usually it's very difficult to know, then you just accept it. And if they talk about this 0.4 and they say, well, this is why it's a 0.4, you can convince yourself, yeah, it needs to be in there. But you could change your scope, because maybe these are intercropping systems done by researchers and intercropping systems by farmers. Well, if it's consistently 0.4, for sure, this would not be adopted. So maybe the distribution of intercropping systems adopted by farmers excludes most of what is below 1. But there will be something below 1 anyhow, because there's always variability. There's measurement error. There is variation between your plots. So some values below 1 are going to be there. So the steps in meta-analysis. So what did Yu Yang do? He formulated the research question: what is the worldwide average value of the LER in intercropping? He defined possible metrics to express the quantities of interest. So the response variable was the LER, and the explanatory variables were species combination. For instance, maize with a legume, or the C3 cereal like wheat or barley or oats with a legume, or the C4 cereal like maize with a C3 cereal. This is also widely used, at least in China is widely used. So he used major categories of species combination, not particular species combination, although this can also be done. And he used nitrogen input as a variable. And there's a variable we came up with in the process, temporal niche differentiation, because we found out that there was a big difference between systems that had simultaneous sowing of the species, where there is full competition all the time, and systems where one species is sown after the other, so that the first sown species has time alone, no competition, and the later sown species usually also has time alone later in its growth, when the first sown species is harvested. And we figured out a simple index to capture this temporal niche differentiation. We defined the scope: worldwide, peer-reviewed studies in English, so excluding everything in Spanish, Portuguese, Chinese. And we defined what information was needed. And we excluded all pot experiments. We excluded all papers that did not report sow crop information, or where the sow crop and intercrop were managed very differently. I don't think we did that very rigorously, because there is some difference there. I won't go into it, no time. We required information on densities, because density is very important for determining intercropping performance. And we wanted the sowing and harvesting dates because of their big influence on land equivalent ratio. Now, this is something that we actually discovered during the extraction and analysis of preliminary data. And we required either the yields or the relative yields, because the analysis of land equivalent ratio is based upon relative yields. So we could have either the relative yields or the yields of the paper, but one of the two needed to be reported. This is the search. So you need to develop a search strategy that will find all the relevant data in the literature. So a literature search was conducted on Web of Science on 21 May 2013. We used the search terms intercrop star or mixed crop or crop mixture or mixed cultivation or polyculture in the title. The search yielded 3,313 publications. 2 samples from these 3,313 publications were analyzed further. The top-cited sample and a random sample. The top-cited sample was made by first ranking the publications according to the citations received between 2003 and 2012, and then screening them one by one until 50 publications had been accumulated that met the inclusion criteria. The second sample of 50 publications was made by simple random sampling from the entire database, excluding the 50 publications already included in the top-cited sample. So it's a very exact description of what we did. This is required in meta-analysis. So it's not statistical, it's procedural. This strategy of doing a top-cited and random sample is totally non-standard for meta-analysis. I've never seen that. That was our idea to do it this way. Because we had the 3,000 papers and it's far too much. I think I'll wrap up in 5 minutes because there's no end to this. There's 3,000 papers out there. So, and we didn't know how many papers you young would be able to work through because we had never done this. We had no experience and it was a lot slower than we had expected. And we thought we cannot afford to miss the well-known papers. So there are some papers by Eric Jensen, by Hogard Nielsen, by Laurent Bédoussac, by Eric Just. So some of those famous papers, we felt we need to include them because if we exclude those, people will not believe our analysis. So we first collected a top-cited sample. When we had that accomplished, and it tells you how bad our foresight really is. When we had accomplished that after maybe 2 years, you young had accomplished that. We thought, yeah, but now we have a very biased sample because these are highly cited papers. Who guarantees us that those highly cited papers are the representative sample of the literature? Maybe those papers are highly cited because they give a high land equivalent ratio. So people like to cite it. So all the intercropping researchers are invested in intercropping and they cite the papers that give a high land equivalent ratio. So then we decided to have another sample of 50 papers. So we did not conceive our whole procedure ahead of time. It's nice to conceive everything ahead of time, but actually we make so much discovery usually during research. Also, as PhD students, you will know that. You learn while you're doing. And you think, oh, I should do it differently. I should do it better. So we developed the methods. What's scientific about it is we tell honestly what we did. So people can see what we did. So it's not that we're hiding how we get the data. So people can repeat this and with what you asked before and say, oh, we find something similar, or we find something different. Then we do selection. Yes.
Did you find a difference in the land equivalent ratio between the two papers?
No. So the two distributions were totally identical, and I was blown away. Because I did not expect that. Because I'm very skeptical by nature, so I doubt everything. So I also doubt the honesty of researchers. I doubt the honesty of researchers citing papers because there are all kinds of biases. But yeah, it's the same distribution. It's the same mean. Here the median is reported 1.17, 1.18. There's really no difference. And we also looked at the relationship between the temporal niche differentiation and the land equivalent ratio. And there was also no difference in this relationship between the two samples. And then we just merged them and analyzed everything as one database because we had to convince ourselves, there's really no difference. So, and there was one difference between the papers, and I realized that when at one point Yu Yang came into the room with the 2 piles of papers that he had been extracting, and one pile was twice as high as the other paper. Which one was highly cited? The big pile or the no, actually the big one. Actually, this is these were papers usually 17 to 20 pages, very extensive reporting, a lot of information. So we convinced ourselves the papers were highly cited because they give a lot of information and people are convinced by the evidence. So it was a big compliment, as far as I'm concerned, for the intercropping literature, because the citation process was totally appropriate, and the highly cited papers are representative. Now, there's no way I can show you all the slides. I can show you all the slides, but I cannot say much about it. But I'll quickly go through and get this finished. Yu Yang then used the same data set and asked a new question. And he was asking a question about the trade-off between cereals and legumes in intercropping. And you've seen a picture like this before, the partial LER of the legume, partial LER of the cereal. Here, the partial LER of the legume is 0, that of the cereal is 1. So you have a land equivalent ratio of 1, because the 2 partials together is the land equivalent ratio. Here is also the land equivalent ratio 1. So all the points below this line is land equivalent ratio below 1. But the points are mostly above the line. So the land equivalent ratio is mostly above 1. But there's a strong negative trend because cereals and legumes are competing. And you can play with the growing conditions in your cereal legume intercrop to get a more desirable outcome. This is the relative sowing time of the 2 species with respect to another. And it has the line for the legume relative yield, the dashed one, and the cereal relative yield. So if you sow the species earlier than the other, so this line means you're sowing the cereal before the legume, and here you sow the legume before the cereal, and here it's the other way around. You see that you get higher relative yield if you give the species a head start. And the relative yield of legumes is across the board is lower than that of the cereal, because cereals tend to be more competitive than legumes. So this is the overarching result. So once you have a database, actually you have a gold mine, so you can use it. And here, Yu Yang is using a different technique to analyze the same data. He's using quantile regression. I was a bit disappointed in quantile regression because I hoped it would give us different insight, but no different insight. So here, very quick, if you have a high land use efficiency in intercropping, then you reduce the land area needed for production. So if you are inputting resources like nutrients and water and other things, actually you do it on a smaller area. So it may reduce your needs for water, for nitrogen and phosphorus, and this can be analyzed. And I think I'll skip this, but there is an index like the land equivalent ratio for fertilizer use. And I'll just skip the explanation. You can read it, read the paper. But we found in one paper that maize soybean intercropping greatly increased the fertilizer use efficiency, but maize peanut intercropping did not increase the fertilizer use efficiency. This very much surprised us because we expected to find the same results in maize peanut intercropping and maize soybean intercropping. The reason is that in maize peanut intercropping, in the experiments, researchers apply as much fertilizer usually to the intercrop as to the sole maize. So even though there is a potential for saving fertilizer because you have a legume in your system, in the experiments, people did not use that. So then when you summarize these experiments, you find no advantage because the researchers did not try to get this advantage. So actually by doing this, we find a limitation in the experimentation by researchers. We wrote that down in a paper and the reviewers didn't like it. This finding is actually not published as such, but I think it's an important criticism of how maize peanut intercropping is done in studies by researchers. Actually, also farmers, because also farmers apply a lot of fertilizer to maize peanut intercropping. This is for phosphorus use efficiency. This was meta-analyzed. I'm just skipping it. And these charts are for capture. And this chart is for conversion efficiency. And we found no difference between intercrops and soap crops. This is the only study so far that has tried to do that. Net effect, I'm going to skip stuff. It's just forever. But this was very exciting. So this is when Chunji became famous because she had her database and analyzed the net effect of intercropping. And she found there was a strong association between the net effect, so the difference between the actual total yield in intercropping and the expected yield, strong association between net effect and temporal niche differentiation and strip intercropping, and actually the use of maize. So she found a major difference between systems that had maize and systems that did not have maize. And why was there such a big effect in systems with maize? Because maize is productive by itself. And those systems also have high inputs, and they're managed to get high inputs. Whereas the systems without maize are mostly in Europe, mostly to achieve lower nitrogen input, but actually with less concern for the total yield. So actually, we found two syndromes of production in intercropping. One trying to get a high yield, usually with maize, and another trying to get lower environmental harm with lower input. And they have different species combination, different input. One is relay, the other is simultaneous. And this illustrates that by doing meta-analysis, you can suddenly stumble on something you were not after. You find something totally new. Okay, there's still many unanswered questions. Intercropping saves water, but how much? Maybe not too much. It reduces pest diseases and weeds. How much? I didn't show anything about that, but Lambert showed a lot about the weeds. We have analysis underway on diseases, and Tao has a beautiful analysis on the effect of variety mixture. You may want to talk to you about it. And well, there are still a lot of things that I'm actually very curious to find out. Word of warning, meta-analysis is a lot of work. Don't think, I see a lot of proposals that say, let's start by doing a meta-analysis. Well, it's a good idea, but don't expect you will finish it in half a year and publish it. Usually this takes a year, and Yu Yang took 3 years before his papers came out. That was also because the supervisors had to learn. It can be faster than 3 years, but it's not fast, it's not easy, but it's very interesting, and you don't get wet in the field. So there's a big advantage there. And it's actually very exciting. And what is very nice is that when you have a meta-analysis, and it's rigorous and that has a lot of papers, then usually reviewers are quite interested because they have the same questions. They also want to know, by how much does it reduce disease? How much water can it save? What affects how much water can it save? These are questions that we have. They need answering. So yeah, it's really worth your time. And yeah, we have some papers, and I thank you very much.